We are discussing about the UML. We'll see the UML, what is UML, brief history of UML and its origins. We'll try to understand the basics of UML and the diagrams and some UML modeling tools. So what is UML? UML stands for Unified Modeling Language. An industry standard graphical language, this UML is for specifying, visualizing, constructing, documenting the artifacts of software systems as well as the business modeling. This UML uses mostly graphical notation to express the object-oriented analysis and design of software projects. It simplifies the complex process of software design. So why UML for modeling? Because a diagram or a picture is equal to 1000 words. It uses the graphical notation to communicate more clearly than natural language, which is somewhat imprecise, and the code which is too detailed or complicated. It makes it easier for programmers and software architects to communicate and for others to understand. And it helps acquire an overall view of a system. UML is not dependent on any other language or technology. UML moves us from fragmentation to the standardization. This is how it started, the year and the version. 1995, it was Unified Method 0.8. There are various other methods and Booch along with OMT. Then it was, more exemplified, covered and standardized. And then we have UML 2.0. So there are types of UML diagrams. In all, major 9 diagrams are there. So use case diagram, this will capture the requirements and it will clarify exactly what the system is supposed to do. It will display the relationship among the actors and use cases. And it is different from traditional flow chart, as you'll see. The class diagram, it shows the static relationship between the classes. That is, it is going to describe the type of objects in the system and various kinds of static relationship that exist among these objects. Then we have sequence diagram. Sequence diagram displays the time sequence of the objects participating in certain interaction. So please understand, we are talking about objects here. In the class diagrams also we are talking about the objects. In sequence also we are talking about objects. And then collaboration diagram, this will display the interaction organized around the objects and their link to one another. State diagram, when the system state changes or object changes its states. So this displays the sequence of states that an object of an interaction goes through during its life in response to certain events or stimuli together with its responses and actions. Then comes the component diagram. Component, this illustrates the organization and dependencies of physical component in a system. Please understand, we are talking about the physical component in a system, a higher level than a class diagram. So let us start with the use case diagram. Here is an actor. This is the boundary in square or rectangle. This is your, say, example, let us take library system. And this is the use case. This is use case. So an actor, these all are actor, client, employer, supervisor. How they are interacting, that means how they are using this system or system aspects. So this is your user or actor and this is your use case. So this is a generalized description of how a system will be used, and it provides an overview of the intended facility or functionality which is required by the actor and the intended functionality which is out to be in the system. In the use case diagram, we saw the core components. First of all, the actor, the role that a user plays with respect to the system, which may include a human user, or you can say he may or she may be a user or a system. That is inanimate physical objects like a robot, an external system that needs some information from the current system. Use case, in this ellipse or elliptical structure, these are the set of scenarios. That is why we call it as use case. A set of scenarios that describe an interaction between a user and the system. Then a use case is a single unit of meaningful work, for example, a login, a register, a place, an order, etc. Each use case has a description which describes the functionality that will be built in the proposed system. For example, use case say order title. You can have a brief description about it. This use case receives order from employee, an employee, or supervisor, then it would return the ordered title. Then comes the system boundary, as you saw with a rectangle. A rectangle diagram representing the boundary between the actors and the system. So here you have the actor and this is your system. Then the association, or you can say use case diagram, holds certain relationship. This is the relationship, a communication between an actor and a use case, which is represented by a solid line. Generalization. What it means is the relationship between one general use case and one specific use case. And this is represented by a line with an triangular arrowhead towards the parent use case, the more general modeling element. That is, a waitress is an employee. A waiter is an employee. This is the generalization. Use case diagram. This include means if you have something bounded in between these angle brackets, double angle brackets. The dotted line labeled this one, beginning at the base use case and ending with an arrow pointing to the include use case. This is include relationship is used to indicate that a particular use case must include another use case to perform its function. So one use case holds inside another use case. For example, this is include, and it uses something. A use case may be included by one or more use cases, so it reduces the duplication of functionality. For example, the list order use case may be included every time when a modify order use case is run. So modify order and list order, in this they can be included. One can include the another. Use case diagram. Extend. This extend means? This is a dotted line labeled extend with an arrow towards base case. The extending use case may add behavior to the base use class. The base class declares the extension points. As you see here, this is the extend. So it is used when exceptional circumstances may be encountered. For instance, a get approval use case may optionally extend the regular, that is modify order use case. This is the extend. This is how you're going to use. There are various, we'll be talking about MS Visio to represent this, how to make this your UML. So this is the use case diagram with what all we have discussed. We have the system name here. This is the system boundary. This is the actor. There are actors like patient, the scheduler, the doctor, and the clerk. And we have certain use case here. These are the scenarios. And this is including, this is include, this is extending, this is extend. So including, extending is also there. And generalization also, you can see there is a generalization also. That is, bill insurance is generalized to pay bill. Okay, now use case diagrams, as we saw that pay bill is a parent use case in the bill insurance. In the child use case, we just saw both make appointment and request medication include check patient record as a subtask. So we have an example of generalization include. Please revisit the diagram again. The extension point is written inside the base case. This pay bill, the extending class defer payment adds the behavior of this extension point, extend. In the class diagram, we have discussed about just now we have discussed about the use case diagram, and that is essentially used in the requirement analysis and modeling, but it can be used elsewhere. But class diagram, each class is represented by a rectangle subdivided into three compartments: name, attributes, and the operations. So modifiers are used to indicate visibility of the attributes and operations. This plus is used to denote the public visibility to everyone. Hash is used to denote protected visibility, like friends and derived classes. This minus means private visibility. No one can visit, no one can access it. So by default, attributes are hidden and operations are visible. So the last two compartments may be omitted to simplify the class diagram. Let us see a class diagram. So we have a name here. The class name is account name. Then we have this minus, plus. And this minus means it is private. Plus means it is public. If you had hash here, it means protected. So these are the operations. As you can see by the round brackets, these are the operations. And customer name is the attribute. This is the example of a class. Let us take a real example in C++. This is a class. Say class name is checking. Now you will have private. This is the access specifier. This is the access specifier. Inside this, you see these two are nothing but the attributes, and all these are the functions. So you have a class, you have attributes, and you have the operations. Okay. Then note this notation of class diagram, there is association. Association represents the relationship between the instances of the classes, and association is a link connecting two classes. So you have class 1, class 2, there will be an association. The association can be bidirectional. Means association are assumed to be bidirectional, like a flight and a plane notation. A unidirectional association means, say, an order and an item notation. So a bidirectional will be a single line like this. A unidirectional will have an arrow, and this arrow is the arrow head is filled. Then we have association in multiplicity and rows. That means this is 1 to star, 1 to many, 0 to 1, and this is star. So what does it mean? Multiplicity means we have 1, that is 1 and only 1. This 0 dot 1 is 0 or 1. M dot n is from M to N, this is a natural language. Star here means from 0 to any positive number. 0 to star means from 0 to any positive number. 1 to star means from 1 to any positive number. So role, what is this role? Say, for example, a given university group many people. A given university groups many people. Some act as students, some would act as a teacher, or a group of people who are regarded as teacher. So a given student belongs to a single university. Student belongs to a single university, and a given teacher may or may not be working for the university at a particular time. 0 to 1 employer, that is 0 to 1, 0 or 1. And then we come to the generalization. Generalization is expressing a relationship among related class. So it is class that includes its subclass. So this is our superclass. These two are subclasses. So these two have a generalized supertype, like a customer. A regular customer is also a customer. A loyalty customer is again a customer. So these two customers, they have generalization as a customer. Then composition. Notation of a class, we have composition. Composition, as you see, this is given by a diamond. This is a whole class. These are the part class. For example, an automobile. An engine is a part of automobile. Transmission is the aspect of automobile. So composition expresses a relationship among instances. Please understand, composition expresses a relationship among instances of a class or related class. It is a specific kind of whole or part relationship. So it expresses a relationship where an instance of the whole class has a responsibility to create and initialize of each part class. So it may be regarded as, say, interface kind of thing. So it may also be used to express a relationship where instances of the part class have privileged access or visibility to certain attributes or behavior defined by the whole class, this one. So the composition should also be used to express relationship where the instances of the whole class have exclusive access to and control of instances to this part classes. Composition should be used to express a relationship where the behavior of part instances is undefined without being related to an instance of the whole, and conversely you can say that the behavior of the whole is ill-defined or incomplete if one or more part instances are undefined. Aggregation. Now in class diagram we have aggregation. Aggregation means what? Aggregation expresses a relationship among instances of related class. So it is a specific kind of container-containee relationship. That is why we are calling it as aggregation. So it expresses a relationship where an instance of a container class, this is a container class, has the responsibility to hold and maintain the instances of each containee class that have been created outside the auspice of the container class. For example, in a bag, we have apples and milk. So bag contains apples and milk. So these are aggregation relationship. This aggregation should be used to express a more informal relationship than the composition expresses. That is, it is an appropriate relationship where the container and its containees can be manipulated independently. So aggregation is appropriate when container and containee have special access privileges to each other. Aggregation versus composition, we have just talked about it. Composition is really a strong form of aggregation, nothing else. Components have only one owner. Components cannot exist independent of their owner. Both have coincident lifetime. Components live or die with their owner. For example, each car has an engine and that cannot be shared with other cars. If the polygon is destroyed, so are the points. In aggregation, they may form a part of aggregate but may not be essential for it. They may also exist independent of the aggregate, less rigorous than a composition. For example, apple may exist independent of the bag. An order is made up of several products. So, but these products are still there even if the order is being cancelled. So we have an example. This is a class diagram example. And if you watch it very closely, these are our classes. Okay, we have a class called order. We have a class called customer. These are all classes. Order line, corporate customer. All these are class. Now we have association here. We have a multiplicity optional 0 star 0 dot 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 1. We have generalization. You see this diagram. This is generalization. So all we have discussed is here. Then we come to the sequence diagram. This is the object interaction. Object interaction, this is sequence means it shows after which will come. So this is a self call, that is a message that an object sends to itself. A message can send a message to itself, we call it as self call. And condition, of course, it indicates when a message is sent. The message is sent only if the condition is true. This is a synchronous, this is asynchronous, this is a transmission delay, this is condition, and this is an iteration, and this is of course the self call. This is object interaction. Object lifespans in a sequence diagram, the lifelines, the dotted lines that extend down the vertical axis from the base of each object. Let me show you it first, then we may discuss it more. Okay, this dotted lines, as you see here, that extends which are extending down the vertical axis from the base of the object. These are the lifelines. So these are lifelines. Messages, these are labeled as arrows, as you can see here, which with the arrowhead indicating the direction of the call. Okay, this is calling here, this is calling here. Activation bar, what do we mean by activation bar? This activation bar is a long thin box on the lifeline. These are method invocation boxes indicating that indicate processing is being performed by the target object class to fulfill a message. This is a kind of activation bar to perform certain action. Then the rectangle also denotes when object is deactivated. Deletion, placing say X on lifetime, object life ends at this point. This is object lifespans. In the sequence diagram, let us generalize it. We have a user. Now there is a message of lookup. It goes to a catalog. Now it again, catalog sends the message back again to the user, title data. Then the message again goes from user, now not to catalog but to reservations, that is okay, not available, reserve the title. And this is all happens till the remove reservation is done by user if some borrow or holding title is going on. So let us see this sequence diagram demonstrate the behavior of object in a use case by describing the objects and the messages they are going to pass. The horizontal dimension shows the objects participating in the interactions. We have certain objects here, and the vertical, this is the horizontal, and this is the vertical. The vertical arrangement of message indicate their order, and the labels may contain a sequence number, as you see here, 1, 2, 6. These are the sequence number to indicate the concurrency. Then we come to interaction diagram. See, in UML there are certain static diagrams, there are certain dynamic diagrams. Then we come to collaboration diagrams. Collaboration, as the name suggests, it shows the relationship between objects and the order of messages passed between them. The objects are listed as the rectangle, and arrows indicate the messages being passed. The number next to the message are called the sequence number. They show the sequence of the message that they are passed between the objects. And this conveys the same information as we did in sequence diagram, but the focus is on the object rows instead of the time sequence. So let us see an example. This is our interaction diagram. As we suggested, this rectangle shows what? This is the numbers again, and these are the numbers. We have the arrows. So this is showing the collaboration between various objects. Then we come to the CRC card, the collection of standard index cards, CRC. Each of which is divided into 3 sections that can be printed or handwritten. What is the benefit of CRC card? These are collaboration cards. So it is easy to describe how class works by moving cards around, allowing to quickly consider alternatives. That is, we have class, collaborators, and responsibility. So this is collaborator, responsibility, and class. Okay, this is the class reservation. Okay, it has certain responsibility to keep list of reserved titles to handle reservation, and we have the collaborators with this class. What are the collaborators? Catalog and user session. So this is a collaborator, means class responsibility collaborator call. How to create a CRC card? We find the class first. We look for main classes first, then find the relevant classes. Then we find the responsibility, because we have to find the class here, then responsibility, then collaboration. That is to know what a class does, what information you wish to maintain about it. Then we define the collaborators. A class often needs to collaborate with one another to get the job done. So collaboration diagram is an example to show the class relationship. Then move cards around. We need to move the cards that collaborate with one another should be placed close together, whereas the cards that don't collaborate should be placed not very closer but far apart. Let us take an example, state diagram. This is a billing example. State diagram shows the sequence of states. States, we are talking about states. An object goes through during its life cycle in response to a certain event, that is the stimuli. Together with its responses and actions, an abstraction of all possible behaviors. So start, if it is invoice is created, unpaid, paying, paid, invoice destroying, end. So all these are the states an object needs to follow. So what are the basic rules for state diagrams? We draw only one object chart at a time. This is very important. In state diagram, we draw only one object chart at a time. A state is drawn as a box with rounded corners. For each state, we draw an arrow to another state if the object can change from one to another in one step. We label the arrow with the event that causes it, and we show the initial state by drawing an arrow from a black filled circle to the initial state. We show the end state by drawing an arrow to a circle with a filled circle inside it. So this is a traffic light example per se. See how it is going on. The event is, various events are going on, and then the transition of the states. So if something happens, it will go from red to yellow, yellow to green. If we have a, say, a car trip sensor or a green timer expires, the positions or the transitions are in the form of state. Okay. Now, component diagram. This illustrates the organization and dependencies of the physical component. Please understand, this is very important. This is in bold. It is talking about the physical components. Has a higher level of abstraction than the class diagrams and usually implemented by one or more classes. We have certain symbols and notation for components. A large rectangle with two smaller rectangle, half inside, half outside on the side. This is the component, a physical component of a system. Component diagram, we have interface. So interface describes a group of operation used or created by the component. So it represents a declaration of a set of coherent public features and obligations similar to, say, a contract, like this. And the dependencies, again, by the dashed arrows. Let us have a component diagram. These are component. These are dashed arrows. And you know there is a kind of relationship. So this order provides a component interface. This is an interface. This is an interface which is a collection of one or more methods with or without attributes, and the account and customer components are dependent upon this interface to order. UML modeling tools, as we said that we'll be talking about certain tools. We have rational rows, the most important and widely used by IBM. We have UML Studio 7.1 or various, by the time I'm talking, the versions may have gone up by Microsoft Corporation, capable of handling very large models. Okay, this is a free, there is a freeware version, you can buy it also. Now we have Microsoft Visio. See, there is no N here. It is Microsoft Visio, just drop N. And we have open source also, like the like Dia, okay, Dia, ArgoML, open source. This is written in Java and various others. So just remember, we are talking about the rational roses, the UML Studio, the Microsoft Visio, the Dia, the Argo UML, and more like this. The Microsoft Visio, as you see here, this is a snapshot. So there are various diagrams as you see here. These are various notations. It is with you. Now you can make it easily. So UML Studio 7.1 is seen like this. All the notations are here. So if we have a poor design like this, we need more heuristics. For that, let us make a cleaner design. And this is possible when you use a UML. I hope you got the idea about UML. Thank you so much. Take care.